Hello everyone, this is Dr. Young, and in this video we're going to talk about heating curves. So we'll take a look at what a heating curve is and figure out how to do some calculations. So we can calculate how much energy is either released or absorbed when you heat up or cool down some sort of object and it goes through a phase change. So right before we're talking about this change in enthalpy, right, this Q, just being the heat released or absorbed during a process. And for us, this has just been heating and cooling things and having them change phases. So in previous videos, right, we used this equation to calculate the Q, the change in energy for our phase changes, and then we use this one for when we change temperature. What's new in this video is just that we're going to do both of these together. We're going to have multiple Q's that we figure out. We're going to have multiple things that we just need to add up so we get a total change in enthalpy, a total change in heat. So here's what a heating curve kind of looks like. This is a representation I got from Wikipedia, and I'll give you another one here in a sec. But notice that here on the y-axis we have temperature, so we're going up in temperature as you get higher and higher, right? So we have 0 degrees for the freezing of water and 100 degrees for the boiling of water. And it should be said, and I'll write this on the next one too, but this would be a heating curve for water. And in theory, most things would have a heating curve kind of like this. Not everything will be exactly like this because some things decompose or they might change depending on the temperature and the pressure and everything. But this is a pretty standard idea of a heating curve, right? Where you start at some low temperature. As you add heat to something, it's going to increase in temperature until you melt it. And then it's going to keep on increasing temperature until you boil it. And then it's going to keep on increasing temperature until you're just done increasing the temperature. Right? So you have this heating curve, and it's not really a curve so much as like a stair-step thing. You've got a diagonal, a flat part diagonal, flat part diagonal. And what this is saying, right, is that this area is when you have just solid ice and you're heating up that solid ice. I know it's kind of weird to think about like you have colder ice or warmer ice, but ice can be like negative 20 degrees or it can be negative 10 degrees. And so as you heat it up, you're going to get up to 0. And then you have this period where you're adding heat. And I'll add this too. It says heat added, but this is your Q. As you add heat, what's happening is that you are going to melt that ice now, right? So there's going to be a period where the temperature of the ice doesn't change, but you've melted it. And then once it's all melted, then it can start heating up again. So you heat it up until you get to the boiling point. And then you start boiling your water. And again, the temperature doesn't change when you boil the water. If you stick a thermometer in a thing of boiling water, it's going to say about 100 degrees Celsius. Until you've boiled all that water and it's all turned into gas, and now you can heat up the gas, right? You can start moving up again as you heat up the gas. So what we're going to do is we're going to kind of analyze this in terms of like, well, which one of these equations do I need to use here, right? So let's look at this first part here, right? Again, we're assuming that this is water. Water is done commonly with these, but again, it could be other substances, right? Where this is the boiling point, right? 100 degrees is the boiling point of water, and 0 degrees is the freezing point. You could say freezing point or melting point of water. That's what Celsius was based off of, was the freezing point and boiling point. And so what we have here is that in this section, right, from when you have your Q from here until here, right, this Q, this change, this heat, it's going to be going into changing your temperature. So I'm going to call this Q1, which is for my first Q. So my Q1 is going to have an equation like MC delta T, right? Because in this area, all the heat that we're putting in is going to change the temperature of that ice. But then once we get up to here, once we get to the 0 degrees, now all that energy is going to be going into melting the ice. So this section right here, I'll call this Q2. Q2 is now going to be this equation, right? Because now we're going from solid to liquid. We're doing a phase change. We're going to use that heat of fusion. And so now it'll be my Q will equal the grams times the heat of, in this case, fusion, right? Because we're melting something right here. So this is where we're going from solid to liquid. But then as we keep on adding heat, right, we're going to get back to Q, and we're going to go to Q3. Now as we keep on adding heat, we've melted all of that ice. So now we're a liquid, and then the liquid's going to start heating up, which is why it starts to move up the y-axis again, and we have a diagonal line again. And so now I'm at Q3, where I have MC delta T again, only now I'm going to have a different heat capacity, right? I didn't put it in here specifically, and we'll talk about this in the next slide, but This heat capacity will be for solid water. This heat capacity will be for liquid water, right? Because we have a different substance now, so I'll have to look those up. But then as I melt, right, I continue melting. Then we get to this point. Oops. We keep on heating it up until we get to the boiling point, and now we're going to go from liquid to gas here. So now we're vaporizing the stuff. So this Q4, oh sorry, this was Q2 over here. This Q4 is going to be, again, the mass times the heat of, in this case, vaporization, because now we're evaporating. And then in theory, you could have a fifth Q as you get up here, and you're just heating up the gas now, Q5. And that would be back to my MC delta T. MC delta T would be my Q5. And so what's going to happen here is that your total, right, your Q total, so I'll put Q total, the total amount of heat, if I wanted to get from, let's say, this point right here to this point right here, right, I wanted to get it from, like, let's just say, negative 20 degrees, and I wanted to turn all of that mass of water into gas at, let's say, 190 degrees. The idea is that I would have to go through all of these equations. I'd have to go from here to here, here to here, here to here, here to here, and here to here. And so what that means is I'd have to add up all of these individual heats, all of these different, these delta H's, or these Q's if you want to call them. So that means I'd calculate my Q1, and I'd add it to my Q2, and I'd add that to my Q3, Q4, Q5. So I'd really do all 5 of these equations, and then I'd add them all up for that total change in heat, whether we gained heat or we lost heat. And so I want to take a look at a couple of examples showing exactly how to do this. I probably won't do one with all 5 just because that's so much work to do at once, and I only have so much space. But let's talk about how we approach this. So let's say we have this question that says, how much energy does it take to raise the temperature of 148.2 grams of water from 22.0 degrees Celsius to 120 degrees Celsius? And I have for you a bunch of information, right? I put those equations up here to remind myself. And then I have the heat capacity of solid water, of liquid water, of water in the gas phase. I have the heat of fusion and the heat of vaporization. These numbers are all things that I'll have to give you, or you would look up. For example, you can either Google it, or there's tables of data in the back of your book. But these are just constants for your substance. And again, our substance is water. All these examples I'm doing are water because it's the most likely one that you're going to see. But if you had a different substance, you would just have different values here, but the process would be the same, right? You'd have the heat capacity of like ethanol or iron or whatever the other substance is that you're being asked about. So again, this is water. And what we're saying here, right, is that we want to raise the temperature from 22 degrees Celsius to 120. So to get my mindset, I'm going to go find 22. I'm going to say, okay, well, 22 is around here. So that means I'm starting here. And I need to get up to 120 degrees. And let's say this is 120 degrees. So I need to get from this point here to here to here. That's what I'm trying to get to, right? 22 degrees Celsius to 120 degrees Celsius. Now, what that looks like to me is that I'm going to have to calculate 3 different Qs. I'm going to have to calculate from here to here, right? That's going to be my Q1. Then I'm going to have to calculate the heat for the phase change. And then I'm going to have to calculate a heat for the next increase in temperature. So I have an increase in temperature, a change of phase, an increase of temperature. And so I'm going to need 3 Qs here, and I need to figure out how do I calculate those 3 Qs. So let's look at our Q1. Q1 is just going from 22 degrees up to 100 degrees. That means I'm going to use my Q equals MC delta T, right? The change in temperature one. So MC delta T. Now my M is just given. It's 148.2 grams. That's easy. The C, right here, this is a liquid. So I need to go find the liquid one. So I'm going to use this version. Right, so I've got 4.184 joules per gram degrees Celsius. And notice that I'm making sure that my units are all the same, right? I'm starting with grams of water. The heat capacity is given in grams and Celsius. So you're going to always make sure that your units are good. And then my delta T here, right? My delta T, remember delta T is always final minus initial. I'll write this over here off to the sides, right? So delta T is T final minus T initial. So in other words, so for my delta T, let me put this, this is fine. So my final temperature, right, is going to be 100 degrees for this little portion. I know I'm trying to get to 120 altogether, but just for this little portion right here, I'm going from 22 to 100. So my final is 100. I'm subtracting 22.0 from that to get my delta T, which I'm going to put in over here, right? And if I do that calculation, I'm just get 78 degrees C. And I'm just going to make sure my units cancel, that I'm doing this all right. So my grams cancel with grams, my Celsius cancels with Celsius. That means my Q is going to be in joules. So my Q1 is going to equal 48365 joules. That's kind of big. I'm going to convert this to kilojoules just because the units are so large. So I'm going to bump that over 3 spots. So 48.365. But I can only have 3 sig figs. So my Q1 is going to be 48.4 kilojoules. You could have left it in joules, just put it to 3 sig figs. I just went to kilojoules because I don't know. I don't like dealing with giant numbers, and it didn't say joules or kilojoules, so I think I'm okay. So I figured out, apparently it takes 48.4 kilojoules for this little section to raise water from 22 up to 100. Great. Now though, now that it's at 100, I have to boil it all, right? So now I have my Q2. And if I'm going to boil it all, now I'm going to use this equation, right? Because I'm going to be heating it I'm not heating it, sorry. I'm going to be changing the phase of it. And here we're going from liquid to gas, which I know is vaporization. So I'm going to use my delta H of fusion. So gram times delta H of vaporization. Sorry, I don't know why I circled fusion when I kept saying vaporization. There we go. So my Q2 is going to equal that same 148.2 grams, but now times the heat of vaporization, which is 2260 joules per gram. Grams cancel, that leaves me in joules, which is going to be, let's see, 60. Nope, just kidding. That is going to be 33493 joules. Again, kind of a big number, so I'm going to move this over to be 334.9 kilojoules, right? Taking into account sig figs. So that's how much energy it takes me to basically vaporize all of that, to go from liquid to gas. But I need to keep heating it up because I'm still at 100 degrees. I need to get it up to 120. And that's where my third Q comes in. So I'm heating again, so MC delta T, where again my mass is that same 148.2 grams. But now, right, I'm heating a gas. This is a gas, so now I need to use this value, the 199 value. So now I'm going to put in a 1.996 joules, and I'm using that one, right, because I'm in a gas now. I'm heating a gas, not a liquid, which is why I changed. And you just always want to make sure you're using the right values. That's, I think, one of the trickiest parts, is making sure you got the right constants for everything. And then my delta T is going from, and I'll just draw this up here, right? My change in temperature, T final minus T initial. My final is 120, my initial is 100. That means my delta T is just 20 degrees. So I'll put in my 20 degrees. Everything cancels. My Q3 is going to be 5.916. Let's just say 12 kilograms. Sorry, not kilograms, kilojoules. All right, so I have everything in kilojoules. This is the amount of heat it would take to do these 3 different steps, right? Heating liquid water, vaporizing that water from liquid to gas, and then heating that gas from 100 degrees to 120 degrees. So how much energy does it take altogether? Well, again, I need to add this all up, right? Because the total amount of energy needed is going to be all 3 of these values put together. All right, that's what I just did. I figured out all 3 of these values. So you simply add them all up, and you should get 389.2 kilojoules. That would be the total energy required to do this process, to go from 22 degrees to 120 degrees. And so you see that we've already done the math in previous videos. This is just putting it together, keeping in mind that as you go from one temperature to another, you might be going through a phase change. And if you do, you need to calculate that. Let's look at another example. This is one I want you to take a crack at here, right? What's the energy? What is the energy change when 6.31 moles of water goes from 84.1 degrees Celsius to negative 18.9 degrees Celsius? So similar question, but I want you to pause and kind of orient yourself, right? Where are you starting? Where are you going? Which of these values are you going to need? Because again, we're going to need more to figure out more than one Q, right? We're going to have at least 2 or 3 or something like that. So I want you to pause and see what you can do with this. Keep in mind that one thing I'll point out now is that you're starting off in moles, but all of these values here are in grams. So I would first step, convert your moles into grams, and then you'll be set to use all these values. So go for it. Okay, so let's take a look at this. Let's do the first thing I mentioned, which is right off the bat, let's convert our moles of water into grams, just so we have our mass amounts. We can use all of these constants here. So 6.31 moles of water, there's about 18.02 grams. Oops, put that on the bottom. See, this is why you always gotta put your units. 1 mole is 18.02 grams. And that's going to equal, for me, it looks like I have about 113.7 grams of water. So that's going to be the amount that I use when I figure out all these Qs. So speaking of the Qs, where am I starting? I'm starting at 84.1, so let's say that's about here. So I'm starting somewhere here, and I'm trying to get to negative 18.9. So negative 18.9 is going to be like down here. And so that means I'm going to be cooling something, freezing something, and then cooling it even more. Those are going to be my 3 Qs, right? So first I'm going to have to cool. Then I'm going to have to freeze. And then I'm going to have to cool again. So again, I'm going to have 3 Qs in this one. So let's get started, right? So the Q1, same thing, I've got my MC delta T. The mass now I just calculated is 113.7 grams. The C, so right here we're in a liquid phase, so that means I'm going to use this 4.18 again. And my delta T, right, if I'm going from 84 down to 0, I'm going to write the delta T up here just because I'm kind of running out of room. The delta T for this part, T final minus T initial, right? We started, the final temperature is 0, and we started at 84.1. Now you'll notice that this gives me a delta T that's a negative value, and that's exactly what we want, right? We dropped 84.1 degrees. This is a negative 84.1 degrees Celsius. And what we're going to see is that when you multiply this all out, right, so I'm solving for my Q1, what that's going to give me is negative 40,000, right, if you calculate this all out. But again, I'm just going to go to kilojoules because the numbers are a little easier to work with. So this would be negative 40.0 kilojoules. But this negative that we got from the temperature means that our Q is a negative value. And does that make sense or not, right? When we cool something down, do we absorb energy or release energy? Remember that the negative sign means you released energy. So yeah, when you cool something down, it releases that energy. That's where the energy goes. That's how it cools, is it releases the energy. So this makes sense. You want to make sure that the signs of your Qs make sense. In that previous example, they were all positive, which meant all those positives, all that energy is being absorbed. And yeah, to heat something up and to boil something and to heat it up again all requires energy. You have to absorb energy for all of those. So this negative Q makes sense. I did my delta T right. That's how the negative comes into play. Now for this next one, we have to be a little more intelligent about how we deal with this equation. So here's my Q2. I just want to warn you, right? So it's a phase change, so delta H. But what we're doing is we're going from a liquid to a solid. We're going from a liquid to a solid. Now I don't have a delta H of crystallization. I don't have a delta H of freezing or anything like that. What I have is the delta H of fusion, and that's going from solid to liquid. And if you remember, what we do is that if you want to change it from solid to liquid to solid, all you do is you put a negative sign in front of it. So now if I want to go from liquid to solid, I do the opposite of the heat of fusion. So this is like the heat of fusion, but it's going to be the opposite. I just put a negative sign in front of there. So now my Q2 becomes 113.7 grams. And so instead of positive 334, it's negative 334, right? Because I'm doing the exact opposite process. I'm not freezing, I am melting. So you just change the sign. But again, it's important that you change that sign there so that you get a negative Q, because again, when things freeze, that is going to release energy. So negative 39112.8 joules, or I'm just going to simplify that using the correct sig figs to 39.1 kilojoules. So that would be how much energy is released when we freeze that water. And then I have to do the last one. We're almost done. Q3mc delta T. Mass is still 113. The C, now I'm dealing with, over here, now we're a solid. Since we have a solid, I'm going to use the heat capacity when it's a solid, which is 2.11. And then my delta T for here, right? So for here, the delta T, remember it's still T final minus T initial. The final temperature is negative 18.9, and the initial temperature was 0. So my delta T again comes out to be a negative number. It's just negative 18.9. So that my Q3 ends up being negative 4. It's a weird 4. Got away from me. Negative 4,491.26 joules. But again, I don't have the right sig figs, and I'm going to put this in kilojoules. So negative 4.49 kilojoules. Again, you don't have to turn this into kilojoules. I just did because I like dealing with smaller numbers, or smaller numbers rather than bigger numbers or more digits. But here's whether you want to report it in kilojoules or joules is totally fine. But then the last step, right, is just to add this up, right? The total heat is just going to be from adding your Q1, your Q2, your Q3, which ends up being negative 83.6 kilojoules. And notice that it's negative, so that means it's being released. This energy is being released. You also, right, remember that our Q is sometimes also interchangeable with the delta H, so you could see that also. So whether you want to report this in joules or kilojoules is irrelevant, but here's how you'd go about that process. Now again, I'm not going to do one for if you had to do all 5, but you can imagine that if you started here and ended up here, you'd have to do 5, right? You'd have a Q1, Q2, Q3, Q4, and Q5 like I showed you at the very beginning. But things to kind of keep in mind. Make sure that your units match. That's kind of, I think, the trickiest thing for this is that making sure that these units make sense with whatever you're given. Because you could see, for example, like it might be kilojoules per mole degree Kelvin instead, right? Might be the units for some of these. And so you might have molar heat capacities or molar heat fusions where this is instead of grams, it's moles, which just means you need to change something in your answer or in the given amounts that you have. So just be mindful of that. Don't just use straight up the numbers that you're given. Make sure that they make sense with the units that you're given. That's, I think, kind of the trickiest thing. But again, we've kind of done all of these types of calculations before, so it's just adding it together. So when you're adding energy or removing energy from something and you have to go through a phase and you change temperature, you do one of these heating curve type problems. Definitely practice this, study up, good luck.